Hello, welcome back to Big Idea 1. This is part 4, talking about periodic trends. Now, periodic trends are something that you're going to want to generally always have in mind. You're always going to want to know what sort of things are the electrons going to do. So periodic trends really will predict the behavior of an electron, and that's important because the behavior of an electron predicts the properties of the atom, how the atom's going to bind with other atoms, therefore build everything that's around us. So there's sort of 3 rules to keep in mind. The first rule, really simple, is position is going to have a lot to do with the behavior of an electron. For example, if this is my nucleus right here, and I've got some electrons right here in the first energy level, because they're so close to the nucleus is going to be positive, of course, and these are going to be negative. There's going to be a very strong attraction between these and those. So essentially, the smaller an atom, the more the electrons will be attracted to it. So smaller atoms, will have stronger electron pulls. And so they'll pull them in closer and closer and closer. The other part of position is, of course, the opposite effect, which is the further you get away, the less it's going to be attracted. So let's say that you're way out here because there's a zillion electrons in between the energy levels. There's just not much pull between this electron way out here and this positive nucleus way down here. So it works both ways. So the smaller it is, that means closer it is. It'll actually be pulling harder on it, and the further away it is, it'll really not have much to hang on to, you see. And the other part of position is that if I was to say, if I had a nucleus, with like 3 protons, okay, that's 3 positive charges. But if I have a nucleus with 12 protons, that's 12 positive charges. So if I have 2 atoms and my electrons are in relatively similar distances from these, the one with 12 is going to have far more of a pull on those electrons than the one with 3. It should make sense. So if these are negative, they're going to be pulled way more closely by the nucleus with 12 positive as the ones with 3. So these are some of the kinds of things you're going to want to look for, and I'm going to go over this in showing you the periodic table in just a second. So position is important. How close is it to the nucleus, and how many positive charged protons does it have? So those 2 things are going to affect the electron. They're going to want to stay closer if it's small and if it has lots of protons. Shielding is the next idea. So shielding is the idea where, let's say you have an atom like, say we have nitrogen. So in nitrogen, your first energy level is going to have 2 electrons, and then your second energy level is going to have another 2 right here. So this is like the 1s, and then this is the 2s. Then in nitrogen you're going to have p orbitals as well. So you're going to have p orbitals swinging around here. Well, this electron right here is attracted and staying here because of this positive nucleus right here. But these electrons are closer to the nucleus, and they're negative, and so what they're going to do is essentially shield the pull of the positive nucleus right here. So they're going to actually sort of cause this to not have as much of a pull toward this because these are negative and they're shielding the positive charges. So in the case of like nitrogen, for example, it's going to have 4 shielding electrons, right? Because all the electrons in the outer p orbital are shielded by the first s orbital and the second s orbital. So you got to have sort of an idea of orbitals and arrangement like we talked about before, and understand, you know, if this is the first subshell, it's going to have 2 shielding electrons. Second subshell, there's 2 here, and there's a possibility for another 6 if you go on to the third energy level, and so on. So shielding electrons are knowing sort of the layers of electrons to know how many electrons are closer to the atom, causing it to be shielded away from that pole. And then the final rule with periodic trends and understanding them is that any atom that has a completed shell is stable, and all atoms want that. So if you look at your noble gases, like let's just look at helium. So helium only has energy level number 1, and it has 2 electrons, so it has a completed shell. So energy level number 1 is completed with 2 electrons in the s orbital, so it's happy, and it's what we call a noble gas. So if you take the next one, lithium, well, lithium has that completed shell, and it also has 1 more electron in the next shell, in the energy level number 2. So it has a 1s, it has those 2 in that completed shell, and then the next shell, which is 2s, has just 1. So lithium is going to be anxious to get rid of this so that it can have this completed subshell. And after this, the second shell is going to take 8 electrons to complete. So most atoms, except for helium and hydrogen, are going to want to have 8 electrons to complete that s and p. And once they have those complete s and p orbitals, they seem to be very happy. So completed shells are what atoms are looking for. Once they have completed shells, they don't seem to want to get rid of their electrons, but in the process to get a completed shell, they will get rid of electrons very quickly and easily. All right, well, let's look at this periodic table right here real quick and just take some of those rules and apply them. So we have different trends, so like we call it atomic radius. So atomic radius is the size of atom. So atomic radius, how big is the thing? And so you just simply follow your rules right here. Well, these are little because they only have like 1 proton, and this one has 1 electron. And of course, we talked about earlier that if you don't have many electrons, they're really close to the positive charges, and so they're going to stick very close. So this is a tiny, 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 tiny little atom. Well, as you move across, it actually gets smaller. And the reason why, if you would look here, like let's say that this is lithium right here. Well, lithium has 3 protons, and look at everything in this row is energy level number 2. None of these electrons will go past shell 2. So what's going to happen is beryllium has 4 positive charges, and its electrons are all in. Here's energy level number 1, energy level number 2. So its electrons only go out to energy level number 2. It has 4. But if you go over here to carbon, carbon has 6. So 6 positive charges. And its electrons are only going to go out to energy level number 2 as well. And so remember, our rule said that the more the positive charges, the closer it's going to pull. So as we go from left to right, the atomic radius will get smaller. And as we go down, each one of these adds a whole nother energy level to the atom, right? So they just get further and further away. So the trend with atomic radius, if we were to draw a little periodic table sample right here, goes like this. It's going to get larger, or smaller, I'm sorry. It's going to get smaller as you go from left to right because of what we just discussed. The amount of protons increases and the electrons are in the same energy level. And as you go down, it's going to get larger. Okay, so that's atomic radius. The next one we talk about is ionic radius. Now, ionic radius is a little bit different and similar in some ways as well. So what's going to happen with ionic radius is essentially if you want to get rid of electrons, like look at these guys right here. So beryllium has energy level number 1, S, is full. And it has 2S, it has 2 of them in the 2S. Well, it needs another 6 electrons to fill energy level number 2, or shell 2. And so instead of trying to get these 6 in this p orbital, it's just going to get rid of these. So if it gets rid of those, what's that going to do to its size? Well, if it had this, and it gets rid of this whole outer energy level, it makes it tiny. So essentially atomic radius is, you would say that cations, because cations are positive, cations equal small. And then an anion, so if we're talking about fluorine right here, so here's fluorine, so fluorine is going to want to actually take an electron, because fluorine has, it has the 1s, it has the 2s, and it has the 2p, and it has 5 of those 2p. And so it's going to want to take and grab us an extra electron, so it ends up with 6 instead of 5. It wants to get that 6th one in there. Well, if you add an electron, you're actually increasing size, because you know, here's your thing. So now you're bringing more electrons in, and that's going to further bring this further away from the nucleus. Now the nucleus is pulling on more negative charges. It's going to make it bigger. So we would say the anions get bigger. Big. All right, so essentially the size would go like this. It would go tiny, 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 and then it would go big. Because right here, we're going to end up with a -3 charge on all these, -2, -1. So as soon as this one's going to take on 3 electrons potentially, and this one 2, and this one 1. So, so that's what we do with atomic radius right there. If we look at some of the other trends, that are important to look at are going to be electronegativity and electron affinity, and let me see, what is the other? Oh, ionization energy, right? So ionization energy, that's kind of an important one for you just to understand, mostly in concept, but it's a really easy idea. Ionization energy is what is the energy it takes to remove an electron. So energy to remove an electron. All right, well, it's the same concept from those rules that we talked about earlier. As you go from this way to this way, what's happening is, remember, the atom is actually getting smaller, because remember, we have the same energy level, but what we're doing is we're adding more and more and more positive charges. The nucleus is getting bigger, but we're all these electrons are still in the same shell. So the more positive nucleus that you add, the closer it's going to pull in, and therefore the harder it's going to be to remove an electron. So the energy to remove an electron as you go from left to right increases. You need to have more and more and more energy to remove those electrons, for the same reason that the atom gets smaller, because there's more positive charges adding, pulling those electrons closer and closer. Now, of course, the opposite would be true when you go down. In this case, going down, if this increases, this would decrease. And the reason why this would decrease is because to remove an electron here, you know, if here's your positive nucleus right here, right? Got this positive nucleus, and you got electrons here, you got electrons here, you got electrons here. Well, all these electrons are shielding the positive charges. They're repelling these in essence, and these are really far away. So every single time you take a step down, you're adding a whole nother shell, which makes those electrons further and further and further away. Just like little magnets, the further you get away, the easier it is to separate them. So the energy to remove an electron as you go down just increases and increases and increases. All right, let's talk about electron affinity. Electron affinity is sometimes difficult for students to understand, but it's really not that difficult of a concept. Electron affinity is just the measure of the change in energy of an atom when an electron is added to it. And so the atom will either give off energy, or it will need energy added. For example, if I was to take helium, and helium is a noble gas, it has 2 electrons, in its outer, it's got a full shell. If I was to say try to add an electron to this, it would make it unstable, and so that would cause me to have to, like, it would take a ton of energy to add to this. Now, lithium, on the other hand, lithium already has this extra electron added, so it's got this 2s1, and this is this 1s2 right here. And so when I take away this electron, it increases the stability of lithium, you see. So anytime an electron is added or taken away, and it increases the stability and, you know, gets it closer to that full shell, we would say that the energy change is negative, in the sense that it's going to give off energy. Ooh, energy off. So if it becomes more stable, energy is released, right? And if it becomes less stable, energy has to be absorbed. So that's what electron affinity is. So electron affinity is talking about the idea of what's the energy change when you add an electron or take it away. Well, of course, electrons are always going to seek to become more stable, so as they get that stability, as they lose or gain electrons to get that full outer energy level, they're typically giving off energy. The last final, and honestly probably the most important one, is going to be the idea of electronegativities. So here's another periodic table for you. So electronegativities is the idea of how strong does an atom attract electrons, right? And so this is really coupled with electron affinity, not electron affinity, ionization energy. So as we go across this way, what happens? Well, the atom, remember, increases positive charges, pulling, so I have more and more and more positive charges. So that increases. My positive charges increase as I go from left to right. And so that causes the electrons to be pulled even stronger and stronger. So my attraction for electrons will increase as I go from left to right. So just like ionization energy, this will increase as I go from left to right, because those positive charges increase, pulling on that thing more and more and more, causing it to have a stronger attraction for electrons. So in essence, if you were to ask which atom has the strongest electronegativity according to this, it would be the one up here. Noble gases, of course, have a full octet, so they don't want to attract any electrons at all. So these ones have the full energy level, so they're not attracting just because they're stable. But look at fluorine right here. Fluorine is going to be super small, and it's going to have 9 positive electrons. Its electrons are not going to go beyond the subshell 2. So it has 9 positive charges, subshell 2, and so it's going to pull those electrons in really strong. So fluorine is going to have an extremely strong electronegativity. Chlorine also has an extremely strong electronegativity. As we go down the periodic table, of course, the opposite is true. As I go down, so if I go from beryllium to magnesium, well, beryllium has all of its electrons in subshell 2, or not subshell, shell 2. And then when you go up to magnesium, you have increased all the way out to energy level number 3, or shell 3. So that's put the electrons way further away. There might be 12 positive charges compared to 4, but the distance now of those electrons is so far away that it's made a dramatic decrease in its ability to pull those electrons to itself. So distance is a big deal. The amount of positive charges is a big deal, but as you step down, that distance is a greater effect. And so electronegativity decreases as you go down, because these electrons just simply get so far away that that atom can't really pull any new electrons to itself. And the last little bit right here that I want to make sure that is understood is the idea of electron ionization energies, as far as multiple ionization energies. So let's look at, let's go back here to like magnesium, for example. So if you look at magnesium, So let's take that off. If you look at magnesium, magnesium has its 1s, and it's got 2 there. It's got its 2s, it's got 2 there. It's got its 2p, it's got 6 there. And it's got its 3s, it's got 2 there. Well, it really wants these 6 more here in the 3p to be full. And to don't have the full shell, you have to have this 3s and 3p. It doesn't have any of these. So in order to do this, it could either add 6 electrons here and bring in 6 new electrons, or it can just lose these 2. Once it's lost these 2, then it's got the full 2s and 2p, right? So it's not going to bring in 6 because that's just hard. So it is going to lose these. It'll lose them one at a time. Now the ionization energy to lose the first one is going to be easier than the ionization energy to lose the second one. So when it loses the first one, it'll have a -1 charge. But then what's going to happen is it's going to have then, so magnesium has 12 positive charges, right? 12 positive charges in the nucleus. See, 2, 4, 6, 7, 8, 9, 10. Wait a minute, was it 10? 12, yes. All right, so 12 positive charges in the nucleus. Oops, get rid of that. And get back to there. So when I lose that first one, now I only have 11 electrons, right? So I have 11 electrons and 12 positive protons. So the pull is strong because I have one more proton than electrons. So it's going to take more energy. So, here's, if this is the energy, to remove this first electron, the ionization energy 1, to remove that first electron, it's going to take less energy than it will to remove the second one. So as you continue to remove more and more and more electrons, the energies go up. But if I was to say try to remove one of these, now if I remove that first 2, then the atom is happy because now it has a full 2. So it's removed these 2 in the third energy level. Now it has a full s. So the jump between the ionization energy to remove the second one and the third one is going to be huge. So let's say it was like 200 joules for the first one. It'd be something like 600 joules for the second one. And then to get to this third one, if I was going to try to remove one of these from the second energy level that's now full, then it's going to be like 2200. So whenever you see ionization energies, whenever you see this big jump right here, this is what tells you that you just went from removing extra electrons in added energy levels to removing one of the electrons in the full stable energy level it had. So that's one way of interpreting ionization energies.